Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to talk about rolling on a horizontal ground. Since rolling motion with fixed direction of angular velocity is a kind of general plane motion, then all the concepts and results of general plane motion are useful in the rolling motion, which are as follows. Total kinetic energy is equal to translational kinetic energy of center of mass plus pure rotational kinetic energy with respect to center of mass axis, and net angular momentum of a system of particles about a point is equal to angular momentum with respect to center of mass plus angular momentum of center of mass with respect to point O. Net torque on a system of particles about point O is equal to net torque with respect to center of mass plus torque acting on center of mass with respect to point O. Net torque about center of mass is equal to rate of change of net angular momentum with respect to center of mass. Now let's take a look at the following example of rolling on a horizontal ground. A disk of mass m and radius r is placed on a rough surface of coefficient of friction mu with zero angular velocity and linear velocity v0. Due to relative slipping, kinetic friction mu mg starts acting, and so acceleration of center of mass is equal to f upon m, that is mu g, and torque of friction with respect to center of mass is equal to r into f, that will be equal to I cm into alpha. Also, friction will act until pure rolling starts, and we want to find out the time when pure rolling starts, total length covered in this time, work done by friction, also linear velocity v, angular velocity omega, and final kinetic energy of the rigid body. Since tau cm is r into f, that is I cm into alpha, so alpha comes out to be 2 mu g upon r, and angular velocity after time t, omega is equal to alpha into t, that is 2 mu g upon r into t, and linear acceleration is mu g, and when pure rolling starts, v is equal to r omega, therefore v naught minus at is equal to v, or v naught minus mu gt is equal to r into 2 mu g upon r into t, and from here we get the time t when pure rolling starts, and that will comes out to be v naught upon 3 mu g. Also v is equal to v naught minus at, that is v naught minus mu g into v naught upon 3 mu g, that comes out to be 2 v naught by 3, and omega is equal to v upon r, that is 2 v naught by 3r. Also length covered in this time t will be equal to v naught square minus v square by 2a, that comes out to be 5 v naught square upon 18 mu into g. Now initial kinetic energy is half m v naught square, and final kinetic energy is half m v square plus half I cm omega square, that comes out to be 3 by 4 mv square or 1 by 3 mv naught square, and change in kinetic energy will be minus 1 by 6 mv naught square, and by work energy theorem total work done, that is also the work done by friction, will be equal to change in kinetic energy, that will be equal to minus 1 by 6 mv naught square. Here it is important to understand that since contact point is changing continuously, so work done by friction cannot be calculated easily by direct definition of work, so work done by friction will not be equal to f into L or mu mgl. Alternatively, we can use the relation LO vector is equal to LCM vector plus R vector cross P vector. Let O is the initial contact point on the ground, therefore net torque about point O, tau O vector is equal to torque of friction plus torque of mg plus torque of normal force n. Since friction force F is passing through point O, its torque will be 0, and net torque by mg and n will also be 0, therefore net torque on the system is 0, and therefore net angular momentum LO vector will be constant, which is perpendicular to the plane of motion. Therefore initial angular momentum will be equal to final angular momentum, or r into mv naught is equal to I cm into omega plus r into mv, that is 3 by 2 mvr. From here we get v is equal to 2 v naught by 3, and sometimes this method is easier than the other method. Thanks for watching Not for Exam, and we will see you next time.